In Lab 2, we discussed the motion of a falling object. The purpose of this lab was to construct two models to describe the motion of a falling object. One model would represent the motion of the object, where the only force acting on it was the force of gravity, while the other model would represent the force of gravity and the force of drag. Once the models were constructed, we compared their motion to the motion of an actual object, a crumpled up piece of paper. In the last lab, we explored Newton's second law when the net force of an object equaled zero, so the object had no acceleration. In this lab, we will also be exploring Newton's second law, but with a net force not equal to zero. We do this by exploring acceleration in terms of an object falling to the ground. For the purposes of this lab, there were two forces acting on our object. One was the force of gravity, equal to the mass of the object times the acceleration due to gravity on Earth, which is 9.81 meters per second squared. The other one was drag force, which can be defined as a force acting opposite to the relative motion of any object. This can be shown as F equals bv squared multiplied by negative j hat, where b is a proportionality constant, v is the object's velocity, and negative j hat gives us the direction of the force. In terms of Newton's second law, the equation allowing us to calculate the final velocity of an object can be written as the final velocity of an object is equal to its initial velocity plus its net force divided by its mass times delta t. Fnet in this equation can take many forms, but in this lab, we look at it in terms of the force of gravity and the force of drag. When we analyze our video and tracker, we can see that the coordinate system is set with the origin at the center of the ball, as well as the ball's falling is set as the negative y direction. Therefore, we can create a position versus time graph shown here, where the ball falls in the negative direction as the time progresses, thanks to the way we oriented our coordinate system. When we construct our first code model, we had to edit several things. First, the ball's mass was the general convention for the mass of a crumpled up piece of paper, which is 4.5 grams. The initial velocity, position of the ball was given from our tracker data, and the initial velocity of the ball was given as 0, because it started from rest. Then we defined our j hat as the vector is 0, 1, 0, and we defined our forces, where the weight force is equal to the ball's mass times gravity multiplied by j, or L force equals mg, and Fnet was just W. Then we wrote our velocity update formula, which is final velocity equals initial velocity plus net force divided by mass multiplied by delta t, as well as our position equation, which is final position equals initial position plus average velocity times time. In this case, the final velocity of the ball is also equal to the average velocity of the ball. When we work with our drag force model, the mass of the ball, as well as the initial position, stays the same, as well as our j hat. However, we do need a proportionality constant in order to give us our magnitude of our drag force. This number was determined by trial and error and measuring our data compared to our tracker data. Then we had to define the two forces acting on our ball. The weight force was just the same as the last one, mass multiplied by j hat multiplied by gravity, but the drag force was the negative proportionality constant multiplied by the magnitude of the velocity squared multiplied by negative j hat again to give us our direction. The sum of our forces was given here, and we use the same velocity update and position update formulas throughout. When we compare our data from our tracker data to our different GlowScript models, we can see that clearly the drag force model was the best predictor of our tracker's success, while the gravity force data, not accounting for drag, went much lower than the others. Many of the assumptions we made throughout this experiment contributed to the difference between the model data and the actual experimental data. First, we only accounted for two forces, drag and gravity, and did not calculate their exact values. The value of B, our proportionality constant, was determined by trial and error and was not exact, and the mass of our ball was given by the general convention for the mass of a piece of paper, and it could have been a little bit different. In addition to this, there could have been more forces acting on the object that we could not have accounted for, including extra air resistance, extra drag, many other forces. What does it mean? The concept of terminal velocity refers to a speed that an object can reach where the force of drag equals the force of gravity. When this happens, the net force acting on the object becomes 0, meaning that there is no more acceleration. When we look at our velocity versus time graphs for both our GlowScript models, we see that neither one shows terminal velocity yet, but the one with drag force has begun to reach it, as we can see the slope of the graph leveling off, and the velocity beginning to become constant. We can see the slope leveling off here. Finally, for our what-if question, if the object was initially thrown downward instead of just being dropped, its terminal velocity would still be the same as if it was just dropped. This is because terminal velocity is not dependent on initial velocity, and depends on the mass, surface area, and gravitational acceleration of an object, all which are the same regardless of whether or not the object is thrown or dropped. If we wanted to show this in our code, we can see this by setting the initial velocity of the ball equal to -5 meters in the y direction, instead of 0, as it was originally. When we run this, we see about the same thing. There is a different position versus time graph model, but the velocity does the same thing where it levels off towards the end, just like in our dropped model.